title of my presentation is Detect Droughts. What do you prefer, the rainfall or soil moisture? So this is the more detailed title, the capability of meteorological drought indices for detecting soil moisture droughts. So this is my last chapter of my PhD work that I done, and my co-supervisors are here with the co-authors Neil McIntyre, Alex Lechner, and Sven Arnold. So these are my co-supervisors, and it's me back in 2015 or 2016 in University of Queensland. So before starting, before moving to the research paper, I will just give a brief idea like why I did this research for my PhD. So I engaged in the Sustainable Mineral Institute in University of Queensland, where in Australia, we know that the mining play a major role in the economy. So in the Sustainable Mineral Institute, we had these six centers. We had the People Center, the Environmental Center, and the Production Center. So when it comes to mining, all the aspects of sustainable mining were subdivided into these six centers, and I was engaged in the Environmental Center, where the Water Center for Water in Mining and the Center for Mine Land Rehabilitation. So that's why I come up with this the research work, because in Australia there are lots of mine work happening, and in the environmental centers of this Sustainable Mineral Institute, they're working a lot in the water as well as the water usage in mining, as well as the rehabilitation of mine lands. So here you can see there are a whole lot of abandoned mines as well as operating mines. So the mining companies, and they are very strict with the rehabilitation of mine lands. So the mining companies, they are working, they have to spend a lot in rehabilitation of mine land after they finish the mine, after they complete it, unless otherwise you won't get the approval for the next mining. Therefore, they are spending a lot. So in Australia, because of the droughts, they have this problem that the rehabilitation, one of main problem for failures in rehabilitation plans is the droughts. So that's why my work comes to the role there, like detecting the recurrence intervals of drought, like how often this drought comes, what are the severities, what are the durations of droughts are very important when it comes to rehabilitation of these abandoned mines. So here you can see, so my work is basically in Eastern Australia. So, you know, Australia is a continent, so it's starting a whole lot of different agroclimatic regions are there, where so here tropical locations, in the middle of the Australia, there are arid locations as well as here the temperate locations. So another problem that they encounter is that if we go with these agroclimatic regions based on, okay, if this area is a tropical climate, so if they are doing the risk assessments and things for thinking it's a tropical location, sometimes they fail because they need site-specific environmental information. When it comes to the droughts, the rehabilitation planners and the managers and the ecologists, they prefer having site-specific environmental data and site-specific recurrent interval curves. So that's why I developed site-specific recurrence intervals for these locations where there are mining sites. So here you can see, like, for the past 100 years, more than 50% of years are under major or minor drought in Australia. So therefore, I developed this recurrence interval curve. And another question comes is, like, when we are dealing with the mining companies, it's the profit. So are we going to simple drought indices or simple methods, or are we going to more complex method? Whether the simple methods are accurate, or can we go with rainfall, or can we work on with soil moisture? Because when it's rehabilitation, we are dealing with the plants. So if we are going with this complex and complex method and observe data like soil moisture, then it's time consuming as well as it's costly. So that is the argument with what type of method we can use. If we are using, can we justify the simple methods by saying, okay, it's cost effective, or do we need more complex methods to have accurate results? So now I will move on to the droughts. So droughts, it's a natural hazard. It's different from all the other natural hazards. So if we take floods, landslides, earthquakes, volcanoes, tsunamis, all these natural hazards, they are like, we know, okay, that we know there is a flood is going on. We know that there is a landslide. And for some natural disasters are very quick, like within, if it is a earthquake, within a couple of minutes it's finished. But when it comes to droughts, it's far-reaching and it's costly because it takes a long time, because we know that sometimes there are droughts for like 5 to 10 years. And also their impact is also very indirect and diffuse. Like for an example, the people like us, like we live in the city and we have the pipe-borne water. Sometimes we don't realize even our country is in a drought unless we are like, we don't realize that we are in a drought until we are in the mid of a drought or we are at the end of the drought. So sometimes we realize there was a drought in last year when the government says, okay, we don't have enough, we can't provide the power for the next couple of months because there was a drought for last year and we don't have the hydroelectricity power in the full capacity. So then we realize, okay, there had been droughts in last year. So because of these differences in droughts compared to other natural hazards, it's difficult to identify droughts, to cost assess the cost as well as to manage the drought. So it's become complex. And also another fascinating thing in droughts is that they have different classification, which you won't get in other natural disasters, such as in droughts, we have socio-economic droughts and you have soil moisture drought. Like sometimes that's why you might get think, is this correct? Like there are hydrological droughts. But when it comes to floods or landslides, we don't have socio-economic landslides. So likewise, I will explain these different types of categories of drought. So this is kind of my favorite model that I created to show different classes of droughts in very simple way. So this is a kind of a perfect situation where we have rainfall, so sunlight is there, and then there are rivers, streams. So this is a normal condition. But when it comes to when there is no rainfall, and then when there is higher evaporation, we call it meteorological drought. So we don't have rainfall and we have higher evaporation because of the solar radiation. So it's a meteorological drought, which is very simple and straightforward. So because of this, there's no rainfall and higher evaporation. You can see that small streams, they will wipe away or vanish away, and the big rivers, they shrink. So then we call it a hydrological drought. And then because of there's no rainfall, there's no infiltration, it reduces the infiltration through the soil because there's no surface water, then the groundwater is depleting, which we call a groundwater drought. So sometimes people have the scientists, they use surface water droughts and the groundwater droughts. By joining these together, we call it hydrological droughts. And then because there's not enough soil moisture in the soil, the plants get dried and then sometimes they die. There we call it's an agricultural drought or soil moisture drought. Afterwards, then because of all these things, so there's no enough water to drink, there's no surface water, the plants are getting die, and the farmers, they will lose their crops and the farm animals will die. And then we call it a socio-economic drought. So these are the different drought classes that you can detect, and then you can estimate when we are estimating the droughts. So here I am, in this paper, we are discussing the meteorological droughts and the soil moisture droughts. And also you can see it's a kind of a hierarchy. It's starting from the meteorological drought, which is very simple and straightforward. And if you are determining the socio-economic drought, then you have to get all the data like rainfall, surface water data, and the agricultural activities that were affected from the drought. So when it comes to socio-economic drought, it's so complicated. So this is the same thing that in more detailed way. So we have the climate variable. So when we don't have precipitation, so we have precipitation deficiency, an increase of transpiration, evaporation, then there will be, we call it a meteorological drought, and then it will affect the stream flows, groundwater storages. We call it blue water drought sometimes. And then there is reduction in water storage in soil or vegetation, then we call it a green water drought. So all these things have their associated consequences of the effects. So all these things can be end up in a socio-economic drought. Another thing that I'm telling that droughts are different from other natural disasters is because based on the practitioners, the way that we are defining the time scale of the drought varies. So if you are a geologist or a paleontologist, the time scale of drought that they are interested in millennia. But when it comes to a hydrometeorologist or agriculture or a farmer, we basically looking into years, weeks, months, or sometimes growing seasons. Like in Sri Lanka, we can go with Yala and Maha season. So that is also another difference, that when we are dealing with droughts as a natural hazard. Okay, so now we are on to detecting the drought. So when we are detecting, we have to detect 3 different things in droughts. So we want to know the severity of the drought, the duration, and the frequency of the drought. So when it comes to the severity of the drought, that means the degree of precipitation deficit. If you are thinking about the meteorological drought, then it's the degree of precipitation deficit. But if you are dealing with the agricultural or socio-economic droughts, then we can go with the degree of impacts that result because of agriculture or socio-economic. That means sometimes you may the economic values of the lost crops, damaged crops likewise. Then the duration. Duration is straightforward, that the time period of the precipitation deficit or the soil moisture deficit, whatever the type of the drought that we are talking, so it is the time period of the deficit. And then the frequency of drought, how often these droughts coming. Is it coming every year? Is it every 5 months, every 10 months, 10 years? Likewise, how often these drought come. So these are the variables that we are detecting when we are estimating the drought. So how we are going to detect the droughts? So as I said, drought doesn't have a universal definition. Therefore, it doesn't have a unified technique or monitoring practice or to quantify drought variables. So the most commonly used method or the commonly used practice is application of drought indices. So these drought indices, they are kind of quantitative measurements that characterize the drought levels by assimilating data from one or several variables or several indicators. So for an example, as I explained previously, the indicators might be the rainfall, evaporation, the soil moisture, surface water. So whatever the indicator, whatever the drought that we are detecting, so we have to get the data for these indicators, and then we are assimilating them. So we are giving them we are finally ending up with a single numeric value. So we can say, look, if you are using a drought index, for an example, if you are using a very simple index, standardized precipitation index, after we get that single numeric value, within the definition, it says, okay, all the values below 0 are considered as droughts. So likewise, we will get a single numeric value. So apart from that, drought indices, there are remote sensing methods that you can detect drought, as well as there are socioeconomic analysis that we can use to detect a drought. So this research paper is basically focusing on using drought indices. And as I said, so the argument is, are we going to go with very simple index or a complex one? Are we going to use the model, or are we going to use physically based physical data? So when in these drought indices, there are more than 150 different drought indices, and they based on the region, the climate, the country, even within countries, there are many different drought indices based on the crop type, likewise. So here I took 40 different drought indices and summarized the input data. So you can see like more than 90%, almost 93% of the drought indices, they are totally dependent on rainfall data. And then there are some drought indices that use temperature, evaporation, river flow, soil moisture, likewise. So the argument is, okay, are we going to go with this with the other 93%? Are we going to use the only rainfall, or are we going to use physically based values? So the problem is now we are dealing with the plants, because it's rehabilitation of these lands. And then so it has to be agricultural soil moisture, because soil moisture is the problem when we are doing a rehabilitation, starting a rehabilitation of plants. So are we going to work with meteorological drought indices, which has rainfall or evaporation, or rainfall and evaporation? The problem is, we know that when it comes to rehabilitation and when it comes to plants, the soil matters a lot. We know that this water holding capacity of the clay is higher than sand. So therefore, we have to consider the soil. And the other thing is, it's again varied with the type of the plant species as well as the growth stage. So if there are drought tolerant species and drought intolerant species, and also if it is seedlings or saplings, they are more vulnerable to drought than the well-established trees. So therefore, the problem, the argument comes, okay, why we should go with physically based value, which is time consuming and costly. So because of the species, plant species, and the type of the soil, many argue that we can't only depend on the meteorological indices, even though they are simple and very cost effective. So then we develop our method. So I put in a flow chart. So first what we did was we did the study for 24 years, and we selected 3 sites, a tropical site, an arid site, and a temperate site. Then we selected the input data are rainfall and evaporation. So we selected 2 different drought indices. The first one is the standardized precipitation index, which requires only rainfall. And then second one is recognized drought index. It needs the rainfall and evaporation. Also, we selected 3 different time scales, 1 month, 3 months, and 12 months. And then we estimated droughts for these 3 locations for past 25 years. So then what we did was, then we use the soil hydraulic parameters, where they are physically based values. So in Australia, there is a database called ESRIS, where you have this measured soil moisture data. If not, you have to measure it. After measuring these data, or if you get the data measured values, you need these values, and then you have to put it into fit it into a water retention curve and estimate another couple of parameters. And then you have to put that estimated parameters into the Hydrus 1D software, where you can generate the soil water potentials for the past 25 years, because we don't have soil moisture data for long time period, especially for 25 years. So, so we simulated monthly minimum soil water values for 2 different depths, for 30 centimeters and 5 centimeters depth. And then we plot the soil moisture data, monthly minimum soil moisture data in yellow, and the standardized precipitation index values in blue. So then we realize, okay, there is kind of a good pattern in between the meteorological drought index values and the monthly minimum soil water potential values. So then we think about checking the correlation. So up to here, we plot the two graphs, and then we thought of getting the correlation between the drought index and the soil water potential values. So then we plot it here. You can see green color is for the one drought index which uses only rainfall. The blue color scatter plots are for the another drought in the other one which use rainfall and evaporation. And then this is 30 means it's for the 30 centimeters depth. Then we realize there is a correlation, but you can't say it is a very good correlation. But looking at it, someone can tell, okay, it has a correlation, so we can go with the drought index values rather than going for measured soil moisture data. So for that, to confirm that, we estimate the failure rate and a false alarm rate for this drought index. We did was, we thought, okay, we will go with drought index value. If somebody is using drought indices, depending only on the rainfall data, what is the failure rate of using it and what is the false alarm rate? So we have the drought index and the model value, physical based values, and we did a performance analysis and we estimate the failure rate. So the problem then comes was that, so what would be the baseline value for a soil moisture drought? Okay, so for drought index, for that mathematical equation, so they have given, okay, below 0, all are droughts. So if it is -1, then it is a mild drought. If it is -4, then it is a severe drought. But when it comes to a soil moisture drought, if you are dealing with the observed soil moisture data, what would be the baseline value from where we are going to tell, okay, from this value, it is a drought, because it depends on the soil parameter, the type of soil, as well as the plant species. So here, so this soil moisture drought can be fallen in between these two lines. So I will explain what are these lines. So, so this is the normal condition. So after a rain, the water is saturated, the soil is saturated from water, the soil, saturated soil. And then slowly, if there is no rainfall and if there is no artificial irrigation happening, then the soil water potential, the soil moisture will slowly reduce. So this point we call the field capacity, where's the best for the plants. So at this point, at the field capacity level, the plants can uptake the water very efficiently. But then if there is no rainfall and no artificial irrigation, then the water soil moisture will reduce and reduce up to a certain point. We call it a permanent built-in point. So at that point, if you up to this point, if you put water again, if you irrigate, or if there is a rainfall, then the plants, even though they wilt, the plants will regrow, not regrow, so it will replenish. So what happens is, if you go beyond this permanent built-in point, then how much you put water, it's not going to come back. So it's, for an example, so if your mom is going for a couple of weeks a trip and asks you to water her garden, and you didn't do it for 1 week or 2 weeks, and you realize, okay, the mom is coming back, now you have to water the plants. And if you are lucky, if it is not reached the permanent wilting points, all the wilted plants will be fresh again by taking the soil, absorbing the soil moisture. But if you are not that lucky, then you will end up in a trouble, because then that means the plants reach its permanent built-in points, and how much you put water, it won't get back again. Then you have to get another excuse for your mom. So that is, so the problem is we don't know what is, from where we are going to take the point. Okay, this is the soil moisture drought. So, so just to be more clear, here, this is the saturation time. So it's saturation. So we normally at the saturation, we call the water potential as 0 because it's saturated. So then it getting negative because it's saturated, and then the water is getting reduced or evaporate. So at this point, we call, so at this level, the saturation level doesn't, it's not very favorable for plants. They can't uptake water efficiently, but then with the gravity, the water is drained. So we call it gravitational water. So after the gravitational water is gone, it comes to this field capacity. Here you can, the field capacity is the best for the plants, and then it's slowly getting reduced if there is no artificial irrigation or rainfall, and then it will come to the wilting coefficient, the permanent wilting point. So here we call, up to this point, this area we call the plant available water. So when you subtract the field capacity from the permanent wilting point, you get the plant available water. And also, after the wilting point, still there is some amount of water that's very tightly attached to the soil particles. We call it hygroscopic water, but you can't, the plants can't uptake them. So this, for the permanent wilting point, so so people, they use the permanent wilting point as a standard. So we have a standard water potential for permanent wilting point. So it is 1.5, negative 1.5 megapascal. So the problem is this 1.5 is the earliest published data of an experimental study by using sunflower. So like literally you can't use that standard water potential value for all the plants. You can't generalize it to all the plants, because sometimes we know that the permanent wilting point varies with the plant species as well as the soil texture. So for example, the potatoes, it's negative minus 1 megapascal, and for wheat, it goes like minus 3 megapascal. So we can't generalize the standard water potential value minus 1.5 megapascal for all the plant species. What we did was okay, so here also you can see, so different soil types, they have different way of the water is getting reduced. So we call it the soil water retention curve. So you can see for sand, silt, and clay. And if you take the permanent wilting point is here, so they have different water content. So the silt and the clay, they have different water content, and also based on the type of this plant, the plant species, and the growth stage, the permanent wilting point might vary. Therefore, we thought of taking the 75 percentile value of the water potential and the 75th percentile value of the drought index as the baseline of a severe drought. So we, as an arbitrary unit, we took it, okay, after this 75th percentile, it's a severe drought and it might affect the plants. So then we estimate the failure rate. So here what we are assuming is, okay, someone, because it's easy to use, someone will use the drought index value. But what will its failure rate? So here you can see for in this area, so the axis, it's blue and brown. I put it blue and brown. That means here it's saturated. So there's no drought in here. When you go beyond with the axis, these areas, when it's -2, -2, it's severe drought. Same as for the soil moisture, when it's come to the hexapascal 3.5, it's kind of a severe drought. So if somebody is using the drought index, so this particular area, that is a soil moisture drought, right? But these four readings were not detected by the drought index. So if somebody is only using the drought index, these 4 particular values were not detected by the drought index, which is a failure rate. So if somebody is only depend on the drought index, they won't detect these three, which is because it's not beyond the 75th percentile of the drought index. So it will be a failure rate. And then we calculate the failure rate. Then the false alarm rate is, okay, so somebody is using the drought index values, but these four events, they are the drought index, the meteorological drought index predicted them as a drought, but it's not actually the soil moisture drought. There is no soil moisture reduction in these four events. Therefore, it's a false alarm. By thinking, okay, these sites are also having the same droughts, the practitioners may arrange the irrigation, but it's not a real soil moisture drought, so it is a false alarm. So by using these failure rates and the false alarm rates, we checked it with all the locations, and we realized that for arid locations, the Berg, the failure rate is quite high. Even for the tropical location, it's like there is a 19% of failure rate. So then we did this performance analysis. So based on the performance analysis, the conclusion is, okay, it's not good to use the meteorological drought indices because there is higher failure rate and false alarm rate. Then the next step was, okay, if we are using the observed soil, the physically based soil moisture values, but still we are using two models to estimate the mean soil water potential. In between, there are many steps. There can be some uncertainties within the model. So because for that, to detect that, we did a sensitivity analysis. So we have the drought index values and we have the physically based value. Then we did the performance analysis. So, and the failure rate is high. Then we thought of doing a sensitivity analysis for the physically based model for these parameters. So these are the parameters that we give into the model. By changing these parameters from 10% to 50%, and then we realized for these parameters, the model is very sensitive. So that means there are a lot of uncertainties. There might be many uncertainties within the model in these steps. So for example, here I use one parameter, the alpha, we insert it to the model. So if we change it to its maximum, here you can see the gray color line is the maximum if we change it to the max. And the blue color line is the default. So there is a significant difference between the maximum and the default value. So in case if there is, when we are inserting the data, there might be uncertainties, and the final outcome, even though we think we have to use the soil moisture data, the method, it has a lot of uncertainties. So therefore, we did another performance analysis to check which one gives the highest failure rates, whether it's the model, the physically based model or the drought index values. So we have this physically based model with the per tube value. That means we change some parameter, we fix one parameter, couple of parameters, and we change one parameter and see what happens to the outcome. Likewise, we did the sensitivity analysis, and then we did estimate the failure rates, and then we subtract the physically based model failure rate with the drought index value failure rate. And what we found was that always the physically based model has a higher failure rate than the drought index values. So because of that, it can be concluded, okay, yes, that we have, if we are going with the agricultural drought, if we are dealing with the plants, yes, it's very important to go site specific, which include the soil, the soil moisture data. But when you are doing this assessment, when you are modeling this soil moisture data, there are a lot of uncertainties where the failure rate might be higher than the drought index values. So the conclusion that the conclusion is that drought index, which use only rainfall, performs better than the drought index that use rainfall and evaporation to detect soil moisture. And then the second one is that the uncertainty of the failure rate and the false alarm rate in soil water retention curve is always higher than the uncertainties of drought indices. So that is the problem. Like, even though the soil water potential values are more important in estimating the agricultural droughts, the failure rate is always higher than the model failure rate is always higher than the drought indices. And then the complexity and the uncertainty in the soil water model encourage to use the simple drought indices. So, and then the model provide that is acknowledged that the model provide physically relevant soil water pressure values, which are species specific for plants. So if we are doing a very sensitive research dealing with the rehabilitation, very like endemic plant species, so it's a very important plant species, not a huge like with whole lot of which you have to do with care, then it's always better to go with the soil water pressure values, the observed soil water pressure values. However, in general, because of the complexity and the uncertainty, the soil water models of the soil water model is always better to use drought indices. So the summary of the presentation, the summary of this article, that is drought is a creepy disaster, and the recurrence intervals of droughts may help for planning a successful rehabilitation while assessing the risk of failure, because we are developing the recurrence interval curves not for a climate region, but for a particular site, particular location. And then, due to the simplicity, meteorological drought indices used for agricultural application, because it's so simple, and in Australia, you don't the rainfall data is freely available, so it's very straightforward. You can directly estimate the meteorological drought index values. However, it is critical to use physically based value to address the plant available water content. As I said, if you are dealing with a very particular plant species, important plant species, then it's always better to go with physically based values. However, the simplest is best. The meteorological drought indices are much better to estimate soil moisture drought due to the sensitivity of the model to its input parameters. So that is the conclusion or the outcome of the paper. So these are a couple of my research, references, and thank you very much for listening, and we'll go for the questions.
Thank you very much, Devanmini. The floor is open for questions. Very interesting, actually. Learned a lot. And yes, so it's open for questions. You can use the chat box, or you can directly ask questions from this speaker. I'll ask a question, Devanmini, till getting settled. Something. Anyway, so the soil moist. Yeah, that what you said is makes sense. Which I mean, something that I never knew. For us, drought is just lack of rain, but as you showed that it can be lack of soil moisture, it could be unavailability of water for a particular species or group of plants. It could be quite variable. Something kind of that I'm thinking lately is the cloud line. You know, like in cloud forest. You know, you have a elevation or gradient, you have a mountain range, and this mountain range would have a variable cloud line that moves up and down depending on the season. In the rainy season, the cloud and fog bank stay low, And in the dry season or in the windy season, if the wind facing towards the mountain, the cloud layer goes up. So the cloud is a like very saturated, humid place. So that will change the, I guess, the moisture content of the forest and the moisture content of the soil. Have you ever done any of such work based on what you talked today? Because this is something I'm thinking of in a future research, where how you the effect of cloud line to the soil moisture and how that affect to the biodiversity. Any thoughts, Devanmini?
Well, actually, with my research, no, I haven't done any related to the cloud line, because in that climates, they don't have the like that much.
Tablelands has a cloud line.
Yeah.
In north of Cranes, in Daintree, in the Queensland tablelands in the north has that effect.
Yeah, so they have this the belt called Brigalow Belt. So it's a mountain range where there is like significantly different climatic climates in between these two in between two sides of the mountain range. Most of the sides,
at certain tablelands, right?
Yeah.
So it has that effect. Sri Lanka, especially in the southeastern bank, like Belihulloya, Fortin Plains, the eastern bank has the same effect. So
yeah, so what we found, but we never think actually I have never thought about it also, like with the cloud line and it would affect, but we know because when we do the analysis, so here we use only 3 sites, but actually I use 14 sites. Within this Brigalow Belt, there is a significant like 2 sites, like that's the thing, like when we take a climatic region, if you use the rainfall data or you use the climate region, then you will get a 1 value, 1 recurrence intervals. But if you are using this site specific data in 2 different locations that across the Brigalow Belt, you will get totally different values. Yes. But it's interesting to think like what would be the best, whether it should go with the meteorological data or the soil moisture value, because with the cloud line, there will be the flow with the trees and the soil will be get moisture, not because of the rain, because that cloud, that one we can't measure.
Exactly. So then I think because in our context, some of the rivers, I think like Kalu Ganga and Kalani Ganga get water directly from rainfall, but the Mahavali Ganga and the rivers in the north, towards north, south, southeast and northwest and all, they get a lot of water from this fog and the mist of the Horton Plains and the Central Highlands. I mean, what you told us today, like, very, very elaborate and very nice. Actually, kind of it opens up a whole scenario, different scenarios where actually the soil moisture should play a very important role in terms of replenishing the fountains.
Yes, but when it comes to Sri Lanka, like still we, even with the meteorological data, we don't estimate the recurrence interval curves. Now one of my MPhil student is doing, who's engaged in the Department of Meteorology, he's working on developing recurrence intervals based on the rainfall data. So in maybe his second or third step would be go with the hydrological droughts and the soil moisture droughts.
All right, thank you very much. We have a question from Vihanga. Vihanga, you can directly ask that. If you have issues with the microphone, I can relay the question.
Yes, I will. Yes. So, madam, I wanted to know that Australia is quite experiencing these bushfires quite often.
Yeah.
So, like, how does these bushfires affect these soil moisture changes, and especially this dryness that occurs with these bushfires? Can they lead to the droughts, as you mentioned?
Actually, when it comes to Australian bushfires, one major factor is that, as per my knowledge, they have a whole lot of eucalyptus trees. So at the dry season, that they evaporate, that vapor is evaporate, And that is one major reason that the huge bushfire starts, and it's very difficult to control because of the eucalyptus vaporize. So your question, Vihanga, whether there's any relation to these droughts and the bushfires, right?
Yes, madam. Yes.
Yeah, so the bushfires comes because of this lengthy droughts, but especially with very dry conditions. That one main point is that it droughts, yes, but one main point is that the eucalyptus vapor that evaporate. Of course, it's because of the droughts, but not very like, it's like anybody can tell, okay, it's because of droughts, it's dry, and then they vaporize, and then the bushfire starts. Yeah, that is the one main reason behind it.
Yes, madam. Thank you.
Hello, Devan. Iomi here. Thank you very
Yes,
much
I
for
am.
your interesting presentation. Actually, how do you see that the drought condition in Sri Lanka? How do you explain in your speciality how it comes and goes time to time? Is
Yeah,
it on
so
monsoon or something else?
yeah, so as I said, like where we, as I said that I'm working with the Department of Meteorology, and we kind of realize that like we think that okay, the Hambantota is the area that has lots of droughts because it's dry, and the Mana, that's very dry, so they have lot of droughts. So that is kind of the idea that the Ratnapura, it's always raining, so there's no droughts. So that is the kind of idea that the general public has. But when it comes to this, it happens because we are dealing with this climatic boundaries. So when we are estimating the droughts in more narrow scale, like if we are going with the Gramaniladari divisions or these DS divisions, or if you are going with site-specific data with the rain gauges, you will get these interesting results where you will realize, okay, Ratnapura is the area that has more droughts than Hambantota. Because when it comes to the drought, it's the below average rainfall, when it comes to the mean rainfall, you average the rainfall, so the drought is a below average rainfall. So when it comes to the Sri Lanka, that is something that general public, the idea that they has is the Hambantota, Mana, Anuradhapura, Palanara, those are the Padaviya, those are the areas that has droughts. Yes, they are dry locations, but when it comes to the droughts, we should not mix the dry locations and the drought, because Sinharaja might be in droughts when it comes to the average rainfall. So we are these days developing these recurrence interval curves for site specific location. Hopefully we will get like interesting results. So most of the time we mixed with dry locations and the droughts. Hope you
Yeah, this is Vindya. Thank you very much for the really interesting presentation, Devan. I just wanted to clarify what you said. So that means areas such as Ratnapura, they get very high rainfalls, maybe for some time, and then the rainfall kind of gets lower. So that is why that happens. Is it so?
No. So
like unless in areas such as Hambantota, the rainfall is kind of
no, it's like this. So we detect the droughts based on the long-term average data. So if we have 30 years rainfall data, we get the long-term average. And that long-term average is the baseline. So if it is like, if it is Ratnapura, so if they have higher rainfall, so for past 30 years, we average the rainfall. So that is the baseline. But now you may realize now, even though there are high rainfalls, but it is below the average.
Yes, yes. Okay. Okay.
It's
Got
not a severe
Thank you.
yeah, it's not,
So
yeah.
okay, so that means in areas such as Hambantota also you have checked this, and so those areas the rainfall has not the average rainfall has not gone beyond the average level
So it's
throughout
like this, yeah. So
these
there are droughts in both in Ratnapura and Hambantota, both they have droughts. But when we consider in the recurrence intervals of drought, how often this drought comes, rather than Hambantota, Ratnapura get more droughts. Yeah, more often droughts. But the thing is that when we think droughts, we think it's a very dry period, there's no water. Likewise, but the drought means just below the average rainfall. If Ratnapura get 2000, just I'm not sure the amount, but if they get 2000 millimeters per year, but now if it is getting 1800, then it can be categorized as a drought.
Yeah. Okay. So it's comparative, right? It depends on the area that we are.
Yeah.
Okay. Thank you very much. Thank you very much.
Devanmini, to add what you said, for example, in Singaraja, inside the Singaraja, the plot that Peradeniya and some of the people here monitor, even very large mature trees are dying, even inside Singaraja, and people outside Singaraja, around Singaraja, villagers say that the Singaraja is in fire now. I mean, fire means not literal fire, but they are dying because of droughts. So I think you explain it very well that so even a very wet place can have droughts, severe droughts, even though you don't see it that way, right?
Yeah.
So I wonder, so the valleys are less susceptible to droughts in that way than the mountain tops, isn't it?
It depends on
stable water. The water table is much lower in hills than the valleys, is it?
That is a good point, sir. So if we are using only the meteorological drought indices, then we will deal only with the rainfall. In that case, we won't detect there is a difference between the valleys and the hills because it's just the rainfall. But if we go to the soil moisture, we will definitely see the differences.
Yeah.
Devanmini, I had a question with Himali. Thank you so much. That diagram was very clear. I really enjoyed it.
Thank you.
Because I had no idea about this, but yeah, that diagram was really good. Just a quick question. So in your model, unless I missed it, I saw that you had used basically rainfall and evaporation, right? Those two are the, is ambient temperature also included anywhere, or does it not matter? Or I was just wondering.
Yeah, so if there are some indices that you can use only rainfall, but when it comes to the evaporation, evaporation is sometimes you have the measured evaporation data, but sometimes the evaporation is calculated based on the temperature.
Right. So, okay. That's what I was thinking is like temperature somewhere embedded in that evaporation. Okay. Okay. That's thanks.
Devanmini, Maheshi has a question here.
So the question is that, can we use any biological indices to measure the drought in Sri Lanka? And are there any studies carried out related to that? For example, what I heard is like spotted dove is a good index for to see whether there's a drought or not. Like in your model, is there a possibility of using biological indices?
You mean that you mean using, like, we know that the lichens sometimes can be used as to detect the air pollution, something like that, right?
Yes.
And you are telling that indigenous knowledge that if I have never heard that thing that the spotted doves can
I don't know whether I'm wrong. I mean, Sampath sir, can you correct me?
No,
Maheshi,
it might be correct.
Hear you. I can't hear you, Maheshi.
I'll type, sir. I'll type.
No, so she was telling that like can we use like biological indicators? So the example she said was that spotted doves can be used as to detect droughts in drought. So like I think it's kind of with the indigenous knowledge, or of course you can use the biological indicators, but then you have to do a survey and you have to compare it with past data and see. But the thing is, there are a lot of other variables, like we don't really know the species diversity is decreasing because of droughts, or whether they don't have their food, or whether there's air pollution or any other physiochemical or the physiological effect. But if you have long-term data with a particular species, then we can model, but that there might be a lot of uncertainties, because that we can't directly tell, okay, this species is depleting or is happening something because of the droughts.
Okay. So I thank you very much for a very clear and extremely interesting presentation, Devanmini. I think this area of research is extremely important for Sri Lanka, without any doubt. So I would like to really encourage you to engage in this, expanding what you are doing right now. Is there anyone else working on drought indices and, you know, in the agricultural sector, in the agriculture faculty in Peradeniya, would you know?
No, madam, I just started, but there are the research scientists that working on those in Department of Meteorology, but no, I don't know anybody from the Peradeniya.
Yeah, if I were you, I would
Madam
check
Professor
up.
Katupota, Madam Professor Katupota once done a seminar on long-term trends in rainfall in Nuwara district at NSF.
In relation to agriculture, or is it?
No, based on just
is in relation to agriculture now. That's what my query is. So just a thought, Devanmini. I mean, I'm outside your field, but as a lay person, I think you can go really a long distance and do really well if you plan this out and, you know, do the right thing. I think isn't it better to relate it to agriculture as well?
Yes, madam. So as in Sri Lanka, they don't, at least we don't have recurrence intervals with the rainfall. So we first thought to have the rain based on rainfall, and then go beyond the surface water and the soil moisture, madam.
Okay, right. So all the best.
Thank you,
Whatever
madam.
that we can do from our end, from the department, please let us know, and we will be 1000% supportive.
Thank you very much,
Thank
madam.
you. Okay.
Okay, with that, thank you, madam, and thank you very much, Dr. Devanmini Halwatura, presenting your work, and not just presenting it, elaborating and giving new insights to the crowd that are not that versed with your area of expertise. I mean, it is the beauty of our department, where we have within the department, we have 4 different parcels which are complementary. At the same time, each can teach a lot to the other 3 and vice versa. So this is a great example, Devanmini. And anyway, I am quite interested in the cloud line and the changes of it, and I have some resources in my disposition to study that. So I think we should discuss a little bit later on that. With that, again, thank you very much for. Here we go.
Yeah, this one just, she helped me a lot, and she just wanted to say hi. Yeah.
Hi. Nice. All right. Anyway, so thank you very much for enlightening us with this whole new window of ideas. I think it will go a long way, as Madam said, you know, in different fields, from environment to wildlife to agriculture to even human health and well-being. So thank you very much, Devanmini, and we'll wind today's session with that. I'm doing this because Maheshi has some connection related issues. We all had a bit of issue today with the connection. So thank you very much again. Thank you very much, everybody, for joining.